Yes, thanks for the introduction. And this is a private stateful information retrieval. It's joint work with Sarva Patel and Pino Persiano at Google. Hope this works. All right, so the scenario that PIR, or private information retrieval, is usually involved in is something like the following, where you have an untrusted server that stores public data, and you have a client that wants to access the data. So the most natural way to do this essentially is to request the index and get the response. However, it turns out that the adversarial server that's just viewing this retrieval can start gathering information. So, for example, this time the client just download this green document. Over time, it can get even more complicated things, such as like this was the most popularly downloaded document, and this document was never downloaded. And it turns out in many practical situations, or practical applications such as encrypted search, this can be problematic. So this led to the study of access pattern hiding storage, or being able to hide the way data is accessed. And there's actually many famous primitives that do this, and they do it in different ways. So like I said, private information retrieval is one way to do this, Oblivious RAM, and there's two more newer constructions called doubly efficient peers and private anonymous data access. The last two actually are more of a theoretical nature. They require superlinear server storage, so I'll just mention them. I won't describe them, but I'll get into the first two now. So, so what is private information retrieval? Probably most of you know this, but I want to go through the details just to underline the difference between private information retrieval and what we do. So the idea essentially is that this client will first generate an ephemeral key or a temporary key. And then it'll do something like encrypt a vector with 1,1 corresponding to the document we want. So here would be the green document. How that encryption works could be fully home encryption. There's other ways to do this, but regardless, you do this and you end up getting back the green document in a way that the server doesn't see which document was retrieved. All right, so the pros of this is that PIR is very simple. It lets multiple clients access simultaneously in parallel without synchronization because the server is literally stateless. It turns out that corrupt clients can leak their private keys without affecting other clients because they're generated ephemerally every single time. If a client crashes or there's a new client that wants to join into the process, well, it can just jump in immediately, essentially. And the server stores each document only once, right? So the big con is that server computation must literally touch every single document, because otherwise, if you don't, the server can quickly deduce that this wasn't the retrieved document. All right, so then there's this other famous primitive called Oblivious RAM or ORAM, which does something slightly different, which I like to describe. It actually has a key that's long-term, and it's required. It's state. It's a client state in some sense, in that this key is very important. Because of what happens is the documents are actually encrypted on the server. And furthermore, the server is actually stateful. So what happens is these documents are actually arranged in some format that's very important and that the client has knowledge of. And what happens is when you do queries, for example, the green document, the state changes. The server state changes and it does something else and it gets the response. So you almost get like a contrast in some sense with PIR. So ORAM gets this beautiful sublinear server computation. In fact, there's a recent result that gets to almost log n essentially. On the other hand, there's this it gets all the cons essentially that PIR had previously. So for example, all clients must share a synchronized state. If any client leaks the private key, well, privacy is all gone. Parallel access requires all this complicated synchronization because the server is stateful. And finally, if a client crashes and loses the private key, or they all lose the private key, there's no hope of getting anything back. So, all right, so let's try to generalize out and see. So it seems like the issue might be something like client state, right? So it seems like the reason PIR has no problem, has all these great benefits, is that there's no permanent client state. There's an ephemeral key, it disappears afterwards. Every session you start a new one, and you get all these great things, no complicated synchronization, etc. On the other hand, this permanent client state for ORAM essentially lets you get this very efficient server computation and bandwidth. You get sublinear, even like literally logarithmic. So this leads to like a very fundamental question: like, can we use permanent client storage in a way that improves the efficiency of PIR, but doesn't sacrifice all these three properties that we really want in any storage system, for example? And the answer is yes. We show that you can do this by introducing a new primitive, which we call a private stateful information retrieval. So the stateful literally means that the client now has some long-term state. Okay, so like I said before, we maintain all the desirable properties of this. However, we essentially are able to use the client state and leverage it in a way that we reduce the server's public key operations to sublinear. I would like to note that the server still does linear computation, but most of it is in plain text operations, but we reduce the public key operations, which are significantly more expensive, to sublinear. And we actually get some other benefits. For example, we're able to move the majority of the bandwidth into offline phases, which is something that previous peers were not able to do because they didn't have state. All right, so this is a summary of essentially what I just described, all these properties. You can get into it more, but you can see that the top two, one is PIR and one is PSIR, which is this paper. And the only difference is that the clients have state. All right, so before I get into our construction, I'll give you the inspiration of where it came from. There's a great result in information theory of essentially coding theory of side information, or PIR with side information. So the idea is something like the following. Let's suppose magically somehow the client had access to this purple document, which we call the side information. The server is completely unaware of which document the client has, but maybe it knows it has one of these documents. So the beautiful result essentially is that suffices to get sublinear, to reduce PIR significantly essentially. So I should also preface with the fact that this work considers information theoretical results. So this is we'll get into that, but essentially the idea is that, okay, we do PIR again, we generate this ephemeral key, which you don't need for information theoretic PIR actually, but so I guess the cool part is that now what you do is the client will create these partitions, but the partition is chosen very carefully in the fact that one of the parts will have so here the client wants to query this green document. One of the parts will contain the query document, the document it wants to query, as well as the side information. So it sends this partition to the server. It also sends an information theoretic PIR for, let's say, the second block. What happens now is this cool part is that the server will also partition its documents. It'll essentially say, oh, okay, I know these partitions. Let me partition them the way I've been told to and sum them up. So now what you've done is you've reduced a PIR from 4 documents to a PIR onto 2 sums essentially, which are of the same size. They're plain text operations. And now if you do the information theoretic PIR, you download the second document. Just simply subtract the purple document and you get the green document as you would want. Right? So like I said, this work considered information theoretic results. So okay, since we're caring more about practical results, we can just replace the information theoretic PIR with the computational PIR. However, there's 2 tricky parts still in that. How do we get the side information? Right? We can't assume it magically appears, and that partition can be quite large, in fact. So how do we deal with that? And essentially, our constructions will focus on solving these 2 problems. All right, so let's get into our construction. So what I'll do now is the first part of this talk or of our construction will essentially say how we generate this side information. So the idea essentially is that this client will have, let's say, 3 buckets, which it'll keep sums of. And the idea essentially is that we're going to generalize the result I said before of this side information by simply saying what I want in these little boxes essentially is square root n minus 1 random items to a sum of square root n minus 1 items. So the idea essentially is if I have this, I could, the document I want to query, I'll just add it in or I'll put it into that partition and deal with it, right? Like this is just a natural generalization of the side information. So we had tried actually many different more complicated ways to actually generate this side information, but it turns out in practice the best way is to literally just stream. So what you'll do over time is essentially, okay, when you're initializing your preprocessing your state, you're just gonna stream the database over time. It's just say, okay, I download the first square root n blocks, and as I said, each of these will be the sum of square root n minus 1 chosen blocks. So here it's 2 blocks. So for example, I download them and I put them into put them in the necessary buckets I want for side information. Do this again, and then I sum one more time, and then one more time. So now after you stream the database, you'll end up with this appropriate side information as we described before. All right, so now how would a query work? It's almost like I described before, but essentially, let's suppose you wanted to query for, I guess, document 2 or block 2 here. So the idea essentially is you're gonna try to add this 2 to one of the pieces of side information I have, or these sums of side information I have. It turns out I can't do it for the first one, obviously, because 2 already exists in there. So what you'll do is you go ahead and essentially skip the first block and you go to the second block of side information. So now what I can do is essentially, like I described before, essentially is to create a partition of this of the database in a way that what I want is I want to partition the 9 blocks into 3 parts, such that one of the parts contains the set 2, 4, and 7. Right. So after I've done this, the server would partition as done, sum and get the result, and I could subtract the result out to get the second block. So how do you do this, right? This seems very complicated, and this is where we consider the crux of our construction is something called Oblivious constraint partitions. So formally, the idea essentially is you get this input constraint set, which was this 2, 4, 7. And what we like to do is we actually like to represent this like a matrix, just for ease of visualization. You get so it would be a square root n by square root n matrix. Since there's 9 items here, it's 3 by 3. And what we're going to do is we're going to represent each row as a part. So the first row is the first part, the second row is the second part, the third row is the third part. So what essentially the goal of this is to somehow convey to the server some partition where we take the constraint set, randomly permute it, pick a random row, and embed it. The rest of the rows, it doesn't matter. Pick anything you want and randomly distribute them. But for security, obviously, we don't want the server to know which of the parts had the constraint set that was the input, so we have to hide that. Otherwise, the problem is actually quite simple. And we also want to do this in a way that's, very communication efficient. We don't want to send this whole matrix across. Instead, we want to send maybe something like square root n keys or something, which is what we'll achieve. All right, so how do we do this? Well, like I essentially described, what we do is we initialize the set of all remaining items, which is the original database of 9 items. We essentially permute the constraint set in some random order and place into a random row of the matrix. And now the goal essentially is to somehow place the rest of the items into the matrix in a random order without essentially violating this constrained row. And it's actually quite simple in some sense from conceptual point of view, is that what we do is for each column, we're going to generate a key. Let's say a hash key. So the client generates a random key, and it's gonna just literally start evaluating from 0 onward until it finds 3 different items. So 3 different values. It goes 6, 1, 6, and 2. And I should note that the output domain of this hash essentially is the size of the remaining items. So this output is essentially going to be the index. It's going to give an index to the remaining items. So what happens is we do this. Eventually, we find 3 unique items in 3 unique values of evaluation. So we throw out any duplicates. And now, okay, what we really want is we have to look at the last value because we want to make sure. So what we're going to do is we're going to take these values essentially embedded into the first column. What we have to do is make sure that that we don't violate this constrained row. So what we do is we're going to just focus on the last item. And we somehow need to make this equal to 4. All right, well, let's see. These were generated randomly in a random Oracle model. So, okay, we could just actually compute some adjustment value, literally. This adjustment value will be random since even though the output was fixed, the input was random, so this other value is random. And essentially here, I would just add 2 to every value. So what I do is, then when I do this, I can essentially completely fix the first column. And this adjustment value also becomes part of the key. So we can repeat this process. Now we just take the remaining items, remove the ones we just added, and start again, essentially. So the next time you do this one more time, you generate a new key. I guess one point that we like to note is that in the first time, it looks like we might just be getting values. So we actually got the values, but those values are actually pointing to indices in the remaining item set. So it just so happens in the first column that the value, so 8 points to number 8 in the remaining item set. But now what we're going to do is we're doing the hashes over the output of the number of remaining items. So we repeat this essentially. So this time we're lucky we get 3 unique items right off the bat, or 3 unique integers right off the bat. Again, now we want to somehow make this 5 equal to this 2, so we compute this adjustment value. And it seems like everything's good. Well, there's a slight problem in that there's actually 2 ways to violate the constrained row. The first way is that I make sure the value I'm going to put in is not what the row says. The other one is I can't actually use any remaining items from the row. For example, that 7 cannot be put into the second column, obviously, because I can't put it into the third column later. So this might seem like a problem, but in reality, this doesn't happen too often, thanks for probability. So just repeat again. Pick a new key, try again. You get something like this, compute the adjustment value, and it works out. And you do this again. So essentially, this is what essentially the client does. But what you can note is that this is actually a deterministic process. So given the above keys, the server can actually repeat the process and get the exact matrix that I just described. And all I only need to send is these 2 square root n values. And that's actually how we convey the partition. So now we want to get the query 2. We pick this 4, 7 as our side information. We send these keys that we just generated before. And of course, like I said, the process is deterministic. The server can, before we do that, we send this computational PIR query for the third sum. So like I described, given these keys, the server can repeat the process essentially and get the partitions and sum them up. That's all plain text operations because this is literally summing. We represent all the blocks in some field. And what we've essentially done is we reduced let's say, PIR on n items to a PIR of square root n items, right? And now you just run the PIR on these items, you get the result, which is the 427. Subtract the 4 and 7, you get 2. You get the block for 2. And okay, so one important thing is that you can't reuse that information, obviously. because then some of the queries start looking similar. So after you use some side information, you discard it, and at some point you'll have to reinitialize and repreprocess client state. But in practice, what we think is that for databases, you have about room for square root n items, so you do this every square root n times, or order square root n times, so your bandwidth is square root n. But what you get to note is that the majority of this bandwidth is actually offline, right? You get very fast online queries, and the fact that summing, like doing plain text operations or plain text sums, is very much faster than order n public key operations, which was done before. And so some experiments, what we did essentially was, this is actually just sort of like a generic transformation, right? You can take any underlying computational or even information theoretic PIR and apply this technique. So this is what we did. So there's this seal PIR construction using homomorphic encryption or fully homomorphic encryption. And we show that by essentially applying it, we get some pretty good results. In particular, the only thing that increases is the client's computation, because we have to generate these Oblivious constraint partitions, but everything else is significantly better in general. Especially, I would like to note that the online bandwidth is much better in general, as well as server computation, because of the PIRs on a much smaller database. And it actually turns out that there's this one of the first PIRs essentially based off of PI or DemGuard, which essentially was considered too slow for larger databases. But what we've essentially done is reduce the database to smaller sizes to a point where actually PI is not only feasible, but actually ends up being, in our opinion, some of the best balanced trade-offs between computation and bandwidth. And we also did this for XPIR as well. So we get XPIR or XPSIR, and we get essentially the same results where we've improved everything. All right, so yeah, in conclusion, I'll go through our contributions again. If you know, essentially, I guess I didn't describe this correctly, but I'll do it now, is that we maintain all the properties of PIR essentially because of the server essentially is stateless, right? We have, so clients can actually reveal their private keys because all states are generated uniformly or independently, and the fact that you can only shoot yourself in the foot by revealing your information. And we get essentially these sublinear public key operations, right? So we don't get sublinear operations in general, but public key operations do usually dominate or typically dominate the computation and bandwidth costs, etc. Yeah, we also get this cool other things, like we get better online costs due to preprocessing that previous PIRs couldn't do, and we essentially get better efficiency in general, even if you consider the amortized costs. All right, thanks for listening. If you guys have any questions?
All right, thanks for your talk. So what's worrying me is when you start throwing away your state every time you use it, which of course you have to do. What happens when you get to your last one?
So yes, that's a good point. You have to use something like, you have to be preemptive in this. You can't like wait till, oh, I have nothing left, I can't do this anymore, because that sort of leaks information in some sense.
Right.
What you essentially do is you pick a point where you know with acceptable and negligible probability you won't run out of items, or you won't be able to solve a problem. So for example, if you're doing square root n, you pick an epsilon, you go 1 minus epsilon square root n blocks. And at that point, after that many queries, you say time to reinitialize.
Okay. And do you literally fetch the whole database at that point, or do you, along with every query, you say, give me? That's
the flexibility of your application, right?
Okay.
If you think, for example, I mean, we would envision this as typically not all bandwidth is the same, right? Bandwidth during the day and on a train in the mobile network is much different than on Wi-Fi when your phone is charging. So you can pick a point during the day, maybe you want. So okay, I did one query here. Time for me to prepare for the next. So for the next epoch, so I'll download maybe 1/1000th of the database, but I'll do it at night, well before I ever need it, right, or something like that. So you can prepare these kind of things. It's very flexible in general because we haven't described when you need to do the offline thing. If it makes sense for you to say, okay, at one point I'm going to chunk off an hour and do all of the pre-processing now, that's up to you as well.
Okay.
Hi, very nice talk. So I was wondering about the communication from the client to the server. So in practice, that's protocol is still better than COPR in the.
Yeah. Let me see.
Because I'm just.
So we have these things down here, but I think actually you're right in the fact that we have our amortize is slightly higher for bandwidth compared when we apply COPR to PSIR. But I was like we just described before, not all bandwidth is equal in terms of cost, in terms of like let's say monetary cost or value or whatever. And doing it online when you're waiting for results is very different than doing it when you're asleep and the phone is charged and on Wi-Fi. So it could work as well. But yeah, that's why we had actually said the PI one was the best in that it actually gives you in some ways the best trade-offs in terms of server computation and bandwidth as well.
Oh, and one more question. So what about if the server's database is dynamic, and do you need to do like?
So we didn't. That's not clearly. That's not something we've done.
Okay, but
that's an open question.
Okay, so like a setup phase is not super expensive, right? So.
Yeah. Depends on what you call super expensive, right?
Okay.
For example, I don't know.
Right. Okay.
Really.
Thanks.
Yeah.
Yeah. So when you delete your site information in the state, do you really need to stream the database again, or can't you sort of mix and match your old site information to get new information?
It's possible, but it's not clear. So there's this question, like for example, you can like store mini puzzle parts, right, and try to combine them together in exponential ways. Hopefully they work out. That could be cool.
There's no reason why you know that it doesn't work, but you also don't know that it does work. Is
so it's something we looked at. We couldn't get it to work.
Fair enough. Thanks.
How big are you? N is the number of records there?
Yeah.
How big is each record?
So we followed the CLPR, and previous thing was 288 bytes. So these are all on the same scale of
88 bytes. So lots of tiny records. Okay. And I'll just throw one more. So in your step where you do CPIR on the square root size database, is there an opportunity for recursing and using this technique itself?
So XPR is recursive.
Well, XPIR, sure.
But XPSIR is also recursive. It doesn't matter at that point, right? Because whatever peer you use, you can use recursion, whatever you want, information theoretic peer. It's just a black box operation.
No, but I'm saying, can you recurse the PSIR construction?
We don't know how to. It's open. We don't know how to do it.